This is your second video in the flipped classroom model that we're starting this year, okay? So in your table of contents, go ahead and get that down, that this is our third entry, limit laws. We're going to talk about the limit laws today. And this is standard L1, and this is your page 9 in your journal of the pages you already have. So our learning target for today says students will apply the limit laws using known limits and graphs to determine the limit of a composite function. So we've been doing limits graphically for the last couple of days. So we want to kind of move into the algebraic sense. So we want to get a little bit more accuracy than just relying on the graph. But there's when we're doing things algebraically, there's laws of algebra that we have to follow when we're dealing with equations. We have laws for limits as well, things we can do to break down a limit in order to solve it algebraically. So we're going to talk about those today and kind of go through some examples, some generic examples. Okay, so the big thing about the limit laws can only be applied if the limit exists in the first place. And that's at the top of the notes. That's very important. Okay, the limit that we're applying the rule to has to exist. Like if it doesn't exist, we can't apply the rule. We're going to have to approach it in a very different way. So it says let B and C be real numbers and let n be a positive integer. B and C real numbers, that just means any number, 1/2, 1, -4/3, and then n being a positive integer, any positive counting number, so like 1, 2, 3, 4, etc. And then let f and g be functions with the following limits. So we're going to say the limit as x approaches c of just a general function of f of x is equal to L, and the limit as x approaches c of g of x, a generic g of x, we don't know what it is k. So we're just going to use those as ways to show our laws. So for examples, we're going to use specific values. So the limit for f of x, for examples, is 4, and the limit for g of x as x approaches c is going to be -5. So we're going to use those consistently in our examples as we go through the rule. The first rule is the scalar multiple. So if we're dealing with a coefficient, and we're going to do this quite often in this class, there's a lot of times we'll take it out of our process, do our process, and then come back and multiply it by that coefficient at the end. It kind of just comes along for the ride. So the scalar multiple says that we can take a coefficient, take it outside the process, figure out what the limit is for the function, and then come back and multiply it at after the limit has already been done. So for example, the limit as x approaches c of -3 g of x. Well, this rule says that we can take this -3 outside of our process, look at the limit as x approaches c of g of x, and deal with g of x, and then come back and multiply it by -3. So according to the top, the limit of g of x was -5. So we have that -3 coefficient. The limit itself was -5, and then we can come back and multiply the second, which gives us 15. The sum and difference rule says that if we're taking the limit of some function that's being added or subtracted, we can take the limit of each function independently, then come back and apply the operation of addition or subtraction. So, for instance, if we have the limit as x approaches c, f of x plus g of x, we can actually take the limit as x approaches c of f of x, and the limit as x approaches c of g of x, and come back and do the addition after. So we have our two limits. So our limit of f of x was 4. Our limit of g of x was -5. I'm going to put that in parentheses. And then we can add them. And when we do that, we get -1. Okay. So that's kind of the sum and difference. Okay, some of these might seem like very simple, but when we start getting into functions, they're going to start to make sense. Okay, why we need them. Okay. So the product one is also the same. If we're taking a product of two functions, we can take the product first, then apply the limit, or we can take the limit first and then apply the product. So for example, if we have the limit of the product of f of x and g of x, we can look at it as the limit as x approaches c of f of x, and the limit as x approaches c of g of x, and then come back and multiply them after the process has been done. So if we take the limit of fx from above, we said our limit of f of x was, sorry, I lost what it was 4. You can't see the top. And then the limit of g of x was -5. And if we come back and multiply that, we get a -20 for that overall limit. Okay. The quotient rule kind of says the same thing. If we're taking the limit of a quotient, so a rational function, most likely, that we can take the limit of the top value, or the numerator, we can take the limit of the denominator, and then come back and divide them after the limits have already been done. So, if we're taking the limit of f of x over g of x, we can first take the limit as x approaches c of f of x, and the limit as x approaches c of g of x, and then we can come back and divide them. Okay, so f of x was 4. From the top, g of x was -5. So we get 4 over -5. I'm just going to rewrite that because I like my negative in front. And we get -4/5. Okay. The next rule is what we call the power rule. Okay, and the power rule says that if we have a function raised to an exponent, so let's say we're taking x plus 3 and cubing it. Okay, we could cube out the function, then evaluate the limit. But cubing out that function is going to take some time. So this rule says that we can actually apply that to that limit to like that x plus 3. And then, of course, whatever that value is, take it to the third power. That's a little bit easier. Okay, so for example, the limit as x approaches c of f of x to the 3/2. Okay. We can also say, in parentheses, sorry, let me get a pen, the limit as x approaches c of f of x first, and then raise it to the 3/2 power. So that rational power, that fraction power, remember the top is the power, the bottom is a root from pre-calc. So if we take that, we get 4 to the 3/2. Okay, if we take the 4 to the third power, that gives us 64. The square root of 64 gives us 8. We can also do it reverse. We can do the square root first. So square root of 4 is 2. And then, of course, 2 to the third power is 8. Both a root and an exponent, and a power are both exponents, so we can do them in any order. Okay, the last rule on here is the constant rule. And what this says is if we're taking the limit of a constant value, like 4, 5, 7, that we're going to get that constant back. Okay, so the limit of a constant is the constant itself. So if we're taking the limit as x approaches 4 or 5, that means we're going to get 5 because it's a constant. And if we think about this in the graphical sense, which is where we've been at for the last couple days, if we graphed f of x equal to 5, we get that horizontal line at 5. So let's say that's 5. Every y value along that line is going to give us back 5. So no matter what x value we approach, no matter where we approach it from, we're always going to get that constant value back. Okay. The last rule, excuse me, is what we call the composite function rule. And this rule says the limit of a composite, so f of g of x, is equal to f of the limit of the inner function. This is true only if that our limit first exists of g of x and that f of x is continuous at that output value. So when we talk about compositions, remember our outputs for one function, the inner function, become the inputs for the outer function. Okay, but the reverse is not true. Just because f of x is not continuous doesn't mean that this rule will not apply. In fact, if we're dealing with any limit that does not exist and we're dealing with a composition, so f of x plus g of x, f of x times g of x, or divided by, if one of them does not exist, that doesn't mean that the limit of the composition is also not going to exist. Okay? When that happens, what we do is we rely on our one-sided limit. So if we have a situation where our function doesn't exist, or sorry, our limit doesn't exist, we're going to rely on the one-sided limit to verify that it truly does not exist after composition. So there's going to be a couple examples at the bottom. Okay. So we have f of x on the left, we have the graph of g of x on the right. So the first one is looking at the limit of f of g of x as x approaches 1. So according to the composition rule, I should be able to first take the limit as x approaches 1 of g of x. Okay. So on g of x, this is my 1 right here. So as I'm approaching, that value is 0. So now my next question is f of 0, does it exist? Is it continuous there? Is there a point there? So if we look at the graph, which is right there, x is equal to 0 right there, we know that f of x is continuous. I don't know how to write tonight. So it is continuous at x equals 0. Therefore, we use this symbol for the word therefore in mathematics. So 3 dots means therefore, if you want to write that down. Okay, because it is continuous, all we have to do is evaluate f of that output, which is now the input for f, which happens to be 2, which means that limit right there is equal to 2. Now if we look at the next one, the limit of f of x times g of x, that's going to that previous page that we talked about the product property. If we look at f of x as x is equal to 2, sorry, as x approaches 2, there's a jump. So this one does not exist. Okay, so because one of them does not exist, we're going to have to approach it differently. Instead of just plugging to or just taking the limit of each and just saying it doesn't exist, I still want to verify that it truly doesn't exist. And we use our one-sided limits to do that. So I'm going to use, let me draw a line there. I'm going to look at the limit as x approaches 2 from the negative side, and I'm going to look at the limit as x approaches 2 from the positive side of, and I'm going to apply the rule. Because even though the limit doesn't exist there, our one-sided limits do exist. So times the limit as x approaches 2 from the negative of g of x. Okay, and I'm going to do the same thing for the right-sided limit. So if we look at that from the negative side, so as we're approaching from the negative side, our f of x is approaching 0. Our g of x, that's at, 2 is right here. Solid line. So as I approach, my y value is about 1. So we're going to call it 1 here. That gives us 0. Okay. Now if we look at the right side, my f of x is approaching 1. My g of x is still approaching 1, and I get 1. Because my left-sided limit and my right-sided limit do not exist, therefore, the limit as x approaches 2 of the composition does not exist. And because there is officially a jump in the composition. Just because there's a jump in one function doesn't necessarily mean there's going to be a jump in the composition of that function with another function. Okay, so we always want to verify that. Okay. And the last one. So again, I'm going to look at the rule. I'm going to look at the limit of the inner piece. So I know these are both f of x, but right now I'm concentrating on the inner piece. So I'm going to look at the limit as x approaches 0 of f of x to confirm that we have a function that's continuous at this value. So going back to f of x, and I'm going to erase this so I can remark it up. going back to f of x, as x approaches 0, from the left and the right, we get 2. Okay. So now if we look at the limit, if we look at f of 2, f of 2 is not continuous, and that's a problem. Therefore, that rule at the top really doesn't exist. So f is not continuous. Okay, so I can't just go and plug it in. I need to look at the limit. So the rule above doesn't apply now, but this is a special case, because if we look at, so remember this 2 value was the output for the inside, but now it's the input. So really what we're doing is we're looking at the limit as x approaches this new input. Okay. Now I want to go back to the graph as we approach 0. So going back to these arrows right here. As we approach 0, the values on this side were below 2. Same thing goes here. The values were below 2. So if we think about it, these values of y now are the input values for our new function. So the values for y were both less than 2. Well, what that means for us is that we are actually looking at the limit as x approaches 2 for the outer limit from the negative side. The negative side only. Okay. And if we think about it, so this is the outer f. Well, this is, in fact, something that we can figure out, because from the left side, we get 0. Because this turned into a one-sided limit, we can officially say that this is 0. But that's only true, that is only true because of what is happening here. Okay, because we're coming up to that point from both left and right. So this is only true. So that's kind of confusing. We're going to need some more practice with that, and that is okay. So what I want you guys to do, that next page, I believe it is page 11. I want you to try some of those problems. And then if you have any questions, come see me the following school day.